Hello guys, welcome to H2O, the A to Z of chemistry. I am Dr. Ritu Johar, your educator for this course, the atomic structure. Today we will begin with lecture 26 from the course, but make sure you have watched the previous ones before viewing this one. Well, in the last lecture, I told you that we are into the last leg of journey where we want to learn about the electronic configuration of elements in this course. Well, in the last lecture, I explained to you the energy level diagram for various orbitals, and now we are moving ahead learning the rules for filling these orbitals in this lecture, wherein after that we will be able to write the electronic configuration. So this lecture rules for filling of orbitals in an atom. So when we want to fill the electrons into the orbitals of different atoms, we do this according to a principle known as Aufbau principle, and this principle is based upon certain things. First, it is the Paulis exclusion principle, then the Hund's rule of maximum multiplicity, and the third is the relative energies of the orbitals. The relative energies of the orbitals is what we have discussed in the last lecture. So this is going to form the basis of the Aufbau's principle. So what is this Aufbau principle? Well, Aufbau is a German word which means building up. And what are we building up? We are building up the orbitals. That means we are filling those orbitals with what? Yes, it is electrons. And the electrons, they are filled in the various orbitals in the increasing order of energies as determined on the basis of their n plus L values, which we learned in the last lecture. Right? So there I even told you that I will give you a way to remember the relative energy of the various orbitals. So let us learn that quickly. Well, in this diagram, if you see, what we are going to do is write the values of n from 1 to 8 in different lines. Okay. What you do is leave one line between 1 and 2, 3 and 4 and so on, and then you start writing the orbitals just like I have written. From one, in front of 1, you write 1s, then 2s, 3s, 4s, 5 and up till 8s. Next, what you have to do is between 2s and 3s, write 2p. 3s and 4s, write 3p, and again move like this ahead. Then coming up to the d orbital, similarly, 3d is going to come between 3p and 4p. And 4d is going to come between 4p and 5p and so on. And next we have the f orbital. So f, where are you going to place? You are going to place it between 4d and 5d, and then 5f between 5d and 6d. Make them written in such a way that you can make lines, slatting lines like this that I have made. Okay. Now if you see, when you have made these lines, you will be able to write the n plus L values. Like for the first line, it is going to be 1, the second line is 2, third is 3, 4, 5, 6, 7, 8. Okay. And all those orbitals which are joined by the same line, they will have the same n plus L values that you learned calculating in the last lecture. Right. For example, 2p. 2 is n and p is 1, so this means 2 plus 1 is 3. Similarly, 3 plus 0 for s, it is going to be again 3. So similarly, n plus L more will be for 3p and 4s and so on. Okay. One thing that you have now learned is that these lines are going to help you know the n plus L values. Next, how do we see now the energies of them? We are going to arrange the subshells according to the n plus L values, and the subshell which has the lower value of n plus L, this is going to possess lower energy. Okay, so we will start with the lowermost n plus L value, that is of 1. So we start from the tail of this arrow, first arrow, move towards the direction of the arrow. The filling of the 1s orbital is going to be first. As you remember, we did this in the energy level diagram also. Now go back again to the tail of the second arrow and you are going to move according to the arrow direction. So you will be filling the 2s orbital after that, and then again go back to the third arrow tail and you will fill first 2p then 3s. Again go back to the next tail, you are going to fill 3p and 4s, and then it is going to be 3d 4p 5s, and then 4d 5p 6s, and again 4f 5d 6p and 7s, and so on. So I hope this is interesting way to remember how we are filling the orbitals according to their increasing energies, right? So the n plus l values. Now always remember what? That the subshell with the lower value of n, they are filled first when the cells, they have equal n plus l values. For example, we have 3p filling prior to 4s. So all this we have already discussed. So I hope this is clear, and now you are comfortable how to remember the energy level diagram, but just drawing this chart like this and then moving on according to it. Okay, so this is the Aufbau principle, where it says that the electrons, they are filled in various orbitals in their increasing order of energies determined by the n plus l value. And this n plus l value, the scheme of filling the electrons according to this n plus l value, this is also called as Bohr-Bury scheme of filling the electrons. Okay. So now there are certain exceptions to the Aufbau principle. For example, we have when we are filling the 4f orbitals. Okay, so before adding an electron to the 4f orbital, a single electron is added to the 5d orbital. Both 4f and 5d, they will have n plus l value to be 7. So according to the Aufbau principle, 4f has a lower value of n, so this has to be filled first, right? But we are saying there is an exception over here, that first fill one electron in 5d, then fill all the 14 electrons in 4f, and then fill the rest of the 9 electrons into 5d. Okay, I hope this is clear, that before adding an electron to the 4f orbital, first a single electron is added to 5d, then 4f is completely filled with 14 electrons, and then we fill the remaining 9 electrons into 5d. And similarly, this we are going to do with the 6d and 5f subshells as well. Next, we have the Paulis exclusion principle. So the Paulis exclusion principle states that no two electrons in an atom can have the same set of values for all the 4 quantum numbers. Right? If you remember, we were doing a question while we learned the quantum numbers that make all the possible sets of quantum numbers possible for an electron. And there we also did the same thing, that 4 quantum numbers for no 2 electrons can be the same, right? If the first 3 are the same, like for a 2s orbital electron, n is 2, l is 0, m is 0. The next also electron, if goes into the same orbital, it will have n, l and m values to be the same. But here what you have to do is then the spin quantum number, this is going to be different for both of them. One will have a plus half value and the other will have minus half value, thus making the set different because of this one value being different. Okay, so this means that an orbital kit can have a maximum of 2 electrons, and these 2 electrons, they must have opposite spin so that the quantum numbers do not remain the same, right? So the inference from here is going to be that an orbital that can have a maximum of 2 electrons. The further applications of this Pauli's exclusion principle is that we can calculate the maximum number of electrons in a subshell and a shell also. For example, if we have the S subshell, L is 0, M is 0. So there S subshell, it has only one orbital, and one orbital can accommodate only 2 electrons. So means the S subshell can have a maximum of 2 electrons. The P subshell, L is 1, M is going to have 3 values. So we have 3 p orbitals, and this means 6 electrons maximum in the p subshell. Then for the D subshell, we have L2. So there are 5 possible values of M. So this means there are 5 orbitals and 10 electrons. Similarly, for the F subshell, there are going to be 7 orbitals and 14 electrons, right? Similarly, for a shell also, we can calculate the maximum number of electrons that can be in it, because we know that the maximum number of orbitals in a shell, this is n square, and in one orbital there are 2 electrons. So the maximum number of electrons a shell can have, this is going to be 2n square. So when n is 1, we have the first shell, the maximum electrons it can have is going to be 2. When it is going to be the second shell, that means it is going to be n square is going to be 2 square, 4 into 2 is 8. So the maximum electrons in the second shell is going to be 8, and this is how we will calculate for the further shells as well. Next, we have the Hund's rule of maximum multiplicity, which is again a very important rule to remember how we are going to write the electronic configuration of various elements, how the filling of electrons is going to take place within the orbitals. So this rule says that the pairing of electrons in the orbitals belonging to the same subshell, that is P, D or F, this does not take place until each orbital belonging to that subshell has got 1 electron each having same spin. What does this mean? That each orbital in the same subshell should be singly occupied first, and the single electron, they should have the same spin, and the pairing is going to start after that. So for example, we can say that we have 3 p orbitals. So the pairing in p orbitals is going to start with the entry of the 4th electron. We have 5 d orbitals. Pairing in the d orbitals will start with the 6th electron. First 5 will go into 1 each in one orbital, right? Similarly, for the f orbitals, the pairing will start with the 8th electron. Now, why is this so? Well, always remember that the fully filled and the half-filled degenerate set of orbitals, they acquire extra stability because of their symmetry, right? So the degenerate set of orbitals means the orbitals which have same energy. So the 3p orbitals, they are equivalent in energy. The 5d orbitals, they are equivalent in energy. The 7f orbitals, they are equivalent in energy. And when these are half filled or fully filled, they acquire extra stability because of their symmetry. So when we want to write the electronic configuration for carbon, which has atomic number 6, how do we do that, right? What we will do is, first we will write 1s2 for the first orbital, that will be finished. Then after that we have 4 electrons left. So we will put 2 into the 2s orbital, right? Again 2 left, they have to go into 2p. So here it is going to be 2px2, 2py0, 2pz0. No, this is not going to be the case. What we have to do according to the Hund's rule of maximum multiplicity is that we will put 1 electron each in the orbitals till they become half filled. Okay, so rather than putting both the electrons in px2, we will put 1 electron in px1, 1 in py, and 2 pz is going to remain empty because we have no further electron to add over here, right? For example, next we have, after carbon we have nitrogen. So the nitrogen, the next electron would go into 2pz. Okay, so that would become 2pz1. The next electron, that would be for oxygen. So oxygen, now there are 4 electrons going into the 2p orbital, and then we would put the next electron again in 2px. Okay, so that would become 1s2, 2s2, 2px2, 2py1 and 2pz1. So I hope this is clear that we have to put the electrons into each orbital of the same subshell till they are half filled. Okay, and then we will start the pairing. Now when the orbitals they are half or less than half filled, the electrons also, the second part of the story was that they should have same spin or parallel spin. Okay, so why is it so? Well, this is because the parallel arrangement of spins is more stable than the anti-parallel arrangement due to the magnetic effect of electron spins. Okay, so remember that we have to first fill them halfway and then start the pairing, and these electrons, they should have the same spin also. The filling of electrons in the degenerate orbitals will take place in such a way that the multiplicity value m should be maximum, where m is defined as 2 into mod of s plus 1. And what is this s? This is the total spin value of all electrons in the degenerate orbitals. So we have seen that the multiplicity value, which is computed this way, this is maximum when we take electrons, filling them up till the half all orbitals singly, and then the pairing starts. Okay, giving you an example in the next slide, we have nitrogen atom, right? So nitrogen atom, the electronic configuration N7, I told you just now also that we have 1s2, 2s2 and 2p3. So how can we fill the 2p3 orbital? This is the way we represent the electrons. Okay, 1s2, this means we have put a square and one electron is having a spin up and the other electron is having spin down. Okay, so both the electrons, they should have opposite spin, that we have done by the Paulis exclusion principle. Then we have 2s2, again both the electrons are going to fill, so one is spin up, the other is spin down. Now comes up to 2p3, what we are going to do over here. So one option is that we fill them singly as told by the Hund's rule of multiplicity, and this can be either a spin up or it can be a spin down, right? The other way is that we have one spin up and two spin down, or two spin up and one spin down. That would not make much of a difference, that will be same case again. And then we have two electrons in one p orbital, one electron in the second one, and leaving the third empty, right? So now you see the multiplicity values for them. First we have to calculate the total spin. Total spin for these 2p3 is going to be half plus half plus half. This makes it 3 by 2. Right? And if you calculate the multiplicity value from this formula, so this you are going to get it as 4. 2 into 3 by 2 plus 1, this comes up to 4. Similarly, if you see for the spin down also, this is going to be minus 3 by 2, but we have to take the mod of s. So this is again going to be 2 into 3 by 2 plus 1. So this becomes 4. Okay. Now taking this as a case, this is going to be plus half. The second two are going to be minus half. Plus half minus half cancel. So we are left with the total value of spin to be minus half. Take the mod of it. You will get the value of multiplicity to be 2. In the next case, again, it is going to be half plus minus half, and then plus half, again half. Okay. So here the values are coming as 2. So these values are less than 4. So this means this is not the right way to write the electron configuration. Right? So we will be putting the electron one each in all the orbitals, and when these orbitals, they are singly occupied, then we will start the pairing. I hope this is clear. This is very important for you to remember this. Now finally what we are left with for this lecture is that you have to understand what is the cause of stability for the completely filled and the half filled subshells, right? They should be completely filled, they should be half filled, but why? So let me explain that to you. First is the symmetrical distribution of the electrons. The half-filled and the completely filled subshells, they have a symmetry, and the symmetrical distribution makes them more stable. Why it makes them more stable is, for example, if you consider the 3D electrons, okay, if we have 5 3D electrons and we put them into different orbitals, this means that they will have equal energy, but they will have a different spatial distribution. Right? They are all oriented along different axes. right? You have studied about dxy, dyz, and so on. So they have a different spatial distribution. And because of this different spatial distribution, the electrons, they do not create that many repulsions amongst themselves. They are not shielding one another. The values of this shielding effect is going to be very small, and hence the electrons, they are going to be more strongly attracted by the nucleus, right? So this is one cause that the symmetrical distribution of electrons make the atoms more stable. So this, I hope the diagram is clear to you. So they are in a different spatial arrangement, hence less of a shielding effect, less of electronic repulsion, and hence more of stability. The other cause for stability is exchange energy. Now what is this exchange energy? We said these orbitals, they should the electrons in the orbital, they should have the same spin. So what this same spin does is that when the electrons, they have same spin, they can exchange positions in between themselves. The first electron going into other orbitals, the other electron coming into its place, and when they exchange their position, some energy is released due to this exchange, and this is called as exchange energy. And more is the exchange energy, more is the stability of these electrons in an atom, right? So this means that the more the number of exchanges that are possible, that is going to cause a stability, and this exchange, this is going to be maximum when the subshell is either half filled or completely filled, right? So let me give you even a diagrammatic representation of that. The relative lowering of energy due to exchange of electrons for the two configurations, this can be calculated as lowering of energy is equal to total number of possible exchangeable coordinates, that is between the set of two electrons with similar spin, into the average exchange energy. So more is the total number of possible exchanges, more is going to be the lowering of energy, and that is going to cause greater stability of that atom. So you can see in the diagram, if the orbitals, they are singly filled, right? So this one electron, this can exchange its position with 4 electrons, right? So these are the 4 ways in which it can exchange its position. The first can go to the second place, it can go to the third place, it can go to the fourth place, it can go to the fifth place. Similarly, the second electron, now this can go into 3 more places apart from the one we've already included in the first exchange. So 3 more exchanges possible for it, going to the third, the fourth, and the fifth. And the next, the third electron, 2 further exchanges possible, and for the last fourth electron, 1 exchange possible. So the total number of possible exchanges is going to be 4 into 3 into 2 into 1. So this is going to be the maximum number you will see when the electrons, they are fully filled or half filled. Whenever the number is less, right, than 5, then also the number of exchanges is going to decrease, and when the number is going to be more than 5, when there is going to be another electron with an opposite spin coming up, so the spins of the spins are going to start cancelling out, so the number of exchanges again are going to decrease. Okay, so the relative lowering of energy, that is going to be because of the maximum exchanges, and that maximum exchanges are for half filled and fully filled orbitals. So we can conclude that the extra stability of the half-filled and the completely filled subshell, this is due to relatively less shielding, smaller Coulombic pulsive energy, and the larger exchange energy. Fine, I hope everything is clear. So that would be all for this lecture. I hope you have understood all the rules very well. How we are going to write the electronic configurations is what we will learn in the next lecture. So stay tuned to our lecture. Wait for the lecture. You can get a notification of that lecture coming up only if you subscribe to our channel H2O and click on the bell icon to get a notification as and when we post up the new lecture for you. So please do subscribe to the channel. If you have any difficulty, you can post at h2ochemistry@gmail.com. Either put it in the comment section also. We will quickly respond as early as possible, I assure you. Right? All your doubts should be cleared and we will try our level best to clear them. Right? So now if you like the lecture, one more thing, please do click on the like link and also do subscribe to the channel. Thank you. Have a nice day. Enjoy yourself. See you again for next lecture.